Great. All right. Well, I think we can get started with our next session. To start us off, we have Peter Melchior from Princeton.
Thanks very much. I will be talking about galaxy models, and this is the work of my group, the Princeton Data Lab. The people who have most contributed to what I'm showing today are circled in red, and so I'll show several of the examples of what we are doing in the lab. What we want to do is we want to look at galaxies and recognize the fact that galaxies are more complicated than we normally have kind of the models for. Traditionally, you would model these galaxies with some form of Sersic model, but that really eliminates learning anything about the substructure of galaxies and kind of the internal structure. It runs into difficulties with things like the overlap between galaxies as you have so-called blending. So we would like to build models that are more complex, more capable than the ones we have. So to have more information that we extract out of the raw data or of these kind of reduced data that can go into catalogs and investigations. If we sharpen this up a little more, then we can see that there is in fact internal structure in those galaxies, even if you can't really tell it's there. And that really brings about kind of a notion or an idea that we would like to extract more information out of these than can simply be done by conventional methods. All right, so the approach that we are taking is that we have a model that is effectively non-parametric. It is free form. Any pixel can do whatever it wants. And we also add the channel direction to make this something that looks like an integral field unit. So basically, it could be the channel direction could be different wavelengths, could be broadband, could be narrowband, could be spectroscopic. It could also be time, right? If we are doing time domain, then the channel direction is very likely time. But the main point here is that we have an intensity in Astro typically called the SED, spectrum energy distribution, for every component, and we have a morphology for every component. So morphology here stands for an image. Can be freeform, any pixel is independent. And then there's a spectrum that can also be freeform. Any parameterization works, but what we do is an outer product of these. That means that there's an intensity variation over the size of this component, and then there's a spectrum that it can assume. That's the parameterization we use. This is free form. It gives rise to a parameterization that looks like this A times S. A stands for all the amplitudes and S for all the shapes. And you have a matrix factorization, a matrix product that you can express this at. We fit this, and in order to fit this for real in actual data, you need to put extra constraints on these. The reason is that you have, for instance, you have these overlapping sources here that you, if you want to look and analyze this, you have difficulties identifying where the light is coming from, which of the sources the light is coming from. And without saying, the likelihood itself will not tell you which of the solutions of attributing light to either of those galaxies is more likely. It's just kind of, it's fine as long as it looks, as long as the resulting model looks like the data, it won't matter. But there clearly are solutions in there that don't look like galaxies. And so traditionally, we've put in constraints like monotonicity or positivity on these. But what I'll show you today is that we transitioned to data-driven priors, and I'll show you why we did. So on top of that, there's something else that you have to do, and that is you're not actually describing the observations. You're describing the model of the sky. So you have to explain with a kind of some form of forward process how your model of the sky differs from the actual observations. And there are many aspects that could be happening between your model of the galaxy that's out there and whatever you can see on an actual observation. Primarily, so we have these rendering operators in here. These could be convolution operators with the Earth's atmosphere with a PSF. They could be resampling operators when you change resolution. They could be even kind of spectroscopic, meaning kind of dispersive elements in there, so that when you work with any form of spectroscopy. So again, we are not modeling the data directly. We have this kind of link between them that is a transformation we understand really well. Astronomical surveys have really invested in characterizing this mapping very, very precisely. So we should exploit that fact. Now, if we put this together, you end up with a code that I wrote about a bunch of years ago called Scarlet. This is being used in the LSST data pipeline as the deblending tool. So it separates galaxies from each other, and it needs to run at scale. We are talking about, give or take, a few billion galaxies. So this needs to be fast. But also appreciate the simplicity. This is one component per galaxy. There is no color variation in those galaxies. It's kind of only an intensity variation. Everyone has an independent color, but there's only intensity variation. There's no color variation within those galaxies. I can show you the residuals, and they're very, very good. But there are problems with this approach. The use of constraints that we are using here gives rise to or requires an algorithm called proximal gradient methods, which is a method where you take a gradient step, which you can see on the top right. And then in order to ensure that the solution obeys the constraints such as kind of positive emitters, you have this proximal mapping, and that's not differentiable. In addition to that, it's hard to come up with realistic constraints for galaxies. Like what kind of constraints do you put? Like what does it mean to look like a galaxy? It's hard to say. And then we also found kind of failure cases in which these proximal gradients run into trapping solutions where the direction the gradient wants to go is directly opposed to the direction the constraint wants to go. And so they deadlock. And you can't actually tunnel your way through this because this proximal mapping is really applying kind of hard transition, hard projections. So there are the gradient would like to level these, but in order to do it, it would have to go negative, and it can't do that. So you're sort of stuck on the trajectory to a better minimum. You're basically stuck. So you can solve all of these things if you replace these proximal operators with continuous prior distributions. So now we are solving for the log of the posterior. So there's now the gradient of a posterior term in addition to the likelihood term. And in the past, we have, for instance, we have a paper from a bunch of years ago where it's a pixel CNN model to describe the galaxy distribution. It was trained on HST data. And you can see that it gives rise to really realistic distributions. And we basically differentiated through that model in order to get the gradients of the prior. So we optimize this for the gradients of the posterior. As you know, that there are more modern ways to do this. This is an example from a paper that will soon come out from my student, Matt Sampson, on a diffusion model to do precisely the same thing. The advantage of a diffusion model is it goes much more directly at the gradient of the prior distribution rather than being sort of a realistic description of the probability. We're going directly for the gradient because the gradient is what we need. Now, to make this, to give you an example here, it's being used in Scarlet 1 on top and in Scarlet 2. It may be hard to tell, but there are kind of some strange effects happening, specifically if the initialization is not good. Here's an example where we intentionally misinitialized the trajectory for the optimization and made one source much too bright. And you can see that these ring-like artifacts just do not disappear, despite the fact that they are highly significant. You get in these trapping solutions and you can't get out of this. Even very, very simple diffusion models. We use a really compact diffusion model and only evaluate the score effectively at temperature 0, will not have this problem. So we have a very, very simple description. We can run this at scale. It's kind of fast enough to run this at scale, and we can totally do that. Now, and it gets us basically out of all of the problems. We haven't found a situation in which the new version of doing these kind of data-driven priors that were learned on high-resolution images or previously deblended images, where they fared worse than what we had before. Now, here's an example. Here's a question that you might ask, namely, how much information do we actually get from the prior versus how much do we get from the data itself, from the observation itself? And so we came up with this idea of computing the Fisher matrix for the likelihood and the Fisher matrix for the prior separately and compare them to each other. And so you can see that in cases when we block out the right side, for instance, all the information comes from the left side, all the data comes from the left side. And we constructed this hallucination score on the left side. If it's blue, it's coming from the data. If it's red, it's coming from the prior. And you can see even on the left side, the outskirts of the galaxies become prior dominated because you have no signal left to work with. So you can quantify how important the prior is in each of these cases. Now, using kind of this stability for the galaxy model, we'd like to extract more. So an example here is to model dust. And so we add a component. So this is a normal emitter. And now we attenuate it with a free spectrum and a free morphology. So the morphology is basically the dust distribution spatially, and then there's a dust attenuation spectrum. And we can do this in practice. Here's an example of a galaxy. You can't tell that there's a dust layer in there, but there is. If you look at the residuals of the model outright, so there's no dust modeling has happened, you can see this reddening, and I can explain why the blue stuff happens, but you can see this reddening here. So there's something like a dusty torus in the midplane of the galaxy. We put this dust model in and only ask for it. Like, we haven't done anything other than this. This is a free-form morphology. We only stabilize the galaxy model to use one of these priors. And so what you see here is the dust model as we can extract it. The dust is, in fact, in many of these galaxies, the leading order correction to the residuals. It's not internal variation, it's the attenuation by dust. Now, I don't have time to go into this. I want to briefly touch upon another element, namely on kind of spectroscopic encoding. One of the difficulties, if you want to go to spectra, is galaxy spectra have different redshifts, and it means that these lines and all of the features move about in the spectrum. And if you were to naively analyze this, you sort of confuse any variation in the spectrum with a variation that's just induced by sort of dry redshifting, just moving this up by putting it to a different redshift. So we came up with an architecture that explicitly has an encoder that is translational invariant. There's an attentive element in here, so you can shift the signal about, and it will sort of respond kind of gracefully under this. So the encoder here is well chosen, but the main trick, the same idea with these rendering operators that we had earlier, it happens here. So we have a decoder that reconstructs the rest frame model, and then we actually explicitly redshift it to go back to the data. That's the same idea as the rendering operators. There's a model that we have internally, and then there's a transformation that we know to do. We know precisely how to do that. It's not complicated. So in this case, we have the redshift. We can just apply it and shift it to where the data actually live. Here's another element that is very important in the context of some of the conversations we've had already and will keep on having during this meeting. And that's the question, what is happening in latent space? So what is actually interesting about this? And in order to make it informative with a generative loss, we needed to add a similarity loss, which says, if the data are similar to each other, modulo redshifting, if the data are similar to each other, they ought to also be similar in latent space. So there's a penalty that penalizes if something is maybe different in data space, but not different in latent space or vice versa. So now there's a relation between the position or between similarity in both of the spaces. And that's enforced specifically, and it makes the latent space much more interpretable. This was, we have a generative loss function, but that makes it almost contrastive in character. What we get out of this is, and I'm just going back for one thing, we then run a normalizing flow on the latent space in order to do something like outlier detection. I'll show you an example just now. All right, so what this does, this extended rest frame model allows you to reconstruct features that you cannot observe, like this emission line on the top that's just outside of the observable window for the spectrograph. It's also robust to these kind of glitches. These are subtraction of the skyline model, so they are kind of induced glitches. And so what you can also do with this normalizing flow model is just ask for cases that have really, really low probability. And you find these kind of really peculiar features. You find blends, you find kind of all sorts of strange quasars, very, very highly attenuated galaxies. And we did not impose whatsoever what an outlier would be. This is completely unsupervised. We just asked for things that are in latent space rare. And lastly, the latent space does have structure. It does have physical structure. You can see kind of continuous variations with redshift and with kind of star formation rate, with dust attenuation. All of these look very, very benign, these distributions. And so the main question that I have is, despite us believing that galaxies are complicated and a lot of physics happens in them, how complex are they really? And that's kind of the question for maybe the discussion today and other conversations. To us, it looks like they're relatively simple. The models we use are simple. They're fast to evaluate. This is important if you want to scale them up. But like, there's an interesting question on how complicated are these? How complicated do they need to be? All right, thank you.
I think we have time for one question from New York. Ashok?
Yeah, hi, thank you. You mentioned for the spectra that you try to make latent space invariable to redshift, but then you showed in the, I guess that's a UMAP later on, that there is redshift dependence.
Right.
So does that work?
Good question. The redshift evolution here is induced by the sample, not induced by the encoder. This is a magnitude limited sample, which means at high redshift, you only see the most massive ones. And they correlate to the ones that have the lowest star formation rate and are the most massive ones that you can get to see. The opposite also true. Go to low redshift and you get to see things that you only can see at low redshift because they're so nearby that you can pick them up. So the evolution here is real, but it's sort of physical and not induced in the latent space by our encoder.
Thanks.
Adrian, are there any questions in Slack?
Yeah, we have a question from Johannes. If you are bored with playing Galaxies, join us in studying AGN. Okay, it wasn't a question.
Noticed. We are interested in AGNs too.
How about the Paris node? Any questions?
Yeah, are there any questions here? Yeah, there's one question from Francois Lenus.
Hi, Peter. I'm curious, what happens if you remove this similarity loss in your autoencoder? Why did you add it?
Yeah, that's a good question. Actually, this one is a good example. If we remove the similarity loss, the UMAP projections still have some regularity to them, but it's much more ordered, it's much more stable if we have the similarity in there. The reason is without the similarity, you can have effectively degenerate solutions where two very similar, in data space, very similar galaxy spectra are encoded to different places in latent space because there's enough flexibility. And the only thing a generator needs to do is take each of these places and generate the same galaxy again. And there's nothing to stop that from happening. And so we found a lot of, think about it as additional stochasticity in latent space induced by the uncertainty which way the mapping goes, which way the encoding actually works. And you can break that by adding this extra penalty.
Okay, thanks. I think we should go on, New York.
Great. So yeah, let's thank Peter again.